Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. In this video, we will learn about sensors and measuring the process state. What elements of the thermodynamic state can be measured? What sensors are available? How should we choose between the different options available? Sensors are chosen by some combination of an instrumentation and control engineer, who is most often an electrical engineer by training, and a process or project engineer, most often a chemical engineer in a process industry plant. The team will make much better decisions if the chemical engineer understands the strengths and weaknesses of the various technologies available. That knowledge will also stand them in good stead when troubleshooting and solving problems in the plant. We rely on the numbers that those sensors give us. We need to know when and why those numbers might be wrong. We will briefly cover the major technologies in this video. For a deeper understanding, please first read the text and then seek out sources like the Instrument Engineer's Handbook by Bela Liptak, which will allow you to explore much more deeply. Measurement technologies. What are the sensor criteria that matter? Accuracy. Does the instrument need calibration, and how readily will that calibration drift? Precision. How many relevant significant digits will this instrument deliver? Reliability. How often will this instrument fail? Cost. Is the cost of a measurement justifiable for your project? Speed. Does this sensor produce data fast enough to use for feedback control and interlocks? And finally, safety. Does this measurement create a risk of operator exposure, toxic release, or fires and explosions? The technologies compared here will differ on one or more of these factors. Temperature is measured in processes using resistance temperature detectors, RTDs, or thermocouples. Thermocouples use a pair of metals welded together. By the principles of electrochemistry, specifically the Nernst law, a potential difference or voltage will exist between pairs of metals that will depend on temperature in a predictable way. Each of the several dozen types of thermocouples has a different pair of metals. The common J-type, for instance, uses iron and a copper-nickel alloy. Every type has a different effective temperature range and a different calibration curve. RTDs measure the resistance to electric current flow through a single metal, which is also temperature dependent. Platinum is the most common metal used. It is very stable and can be used in a range of -200 to 650 degrees C. Both are accurate and repeatable to within 0.1 to 0.2 degrees C. Neither has moving parts, but the thermocouple has a weld, so thermocouples tend to last 5 to 10 years and RTDs 10 to 20 years. RTDs are more expensive, but are simpler to install, more robust, have a wider range, and last longer, so are now the preferred option in most process plants. Temperature probes use thermal wells to avoid contact with the process fluid. See the text. Modern pressure sensors use the measured deflection of a diaphragm, a thin disc of metal, to measure the difference between two pressures. If both sides are connected to the process, we call that a delta P or DP sensor. More often, one side is at a reference pressure. Pressure sensors achieve a precision of 0.1% of full scale. So a sensor with a range of 0 to 100 millibar measures a hard vacuum of 2 millibar at plus or minus 0.1 millibar, while a sensor with a range of 0 to 2000 millibar measures the same 2 millibar at plus or minus 2 millibars. So if you're going to control a vacuum vessel at 2 millibar, you need the former. But you'll need the latter to measure pressure as you pull vacuum and break back to atmospheric pressure of 1013 millibar, which is why quite often you need both sensors. Diaphragms are thin pieces of metal that yield as they flex, particularly at high temperatures. All pressure sensors lose their calibration, and should be on a regular recalibration replacement schedule of no more than 1 to 2 years. See the text for a discussion of DP sensors and isolation for chemical compatibility and maintenance purposes. Flow can be measured in a variety of ways. Rotometers are simple, non-powered applications of fluid mechanics, good to plus or minus 5% and not suited to providing a signal to a control system. Orifice and Venturi meters use Bernoulli effects to correlate pressure drop with flow. The measurement is a volumetric flow, not mass flow, and the pressure drop depends on velocity squared, so low-range flows are measured with poor precision. Long lengths of straight pipe, at least 10 diameters upstream and downstream, are required to avoid biasing the measurement with uneven flow patterns. Plus or minus 1% precision is possible and good accuracy when the device is new and calibrated, but fluid contact will wear out the orifice and the pressure transmitter will drift over time. Turbine flow meters correlate volumetric flow with rotation speed, but require even longer straight pipe for smooth flow lines, at least 15 diameters on each side. They can achieve plus or minus 0.5% precision, but have a lot of moving parts that can wear out. Velocity in a large cross-sectional area pipe can be used to estimate volumetric flow using a pitot tube or a vortex shedding meter. Pitot tubes use the Bernoulli principle to correlate velocity with a measured pressure drop, and vortex shedding relies on the von Karman effect to measure vortices generated by a shredder bar that correlate to velocity. Neither has moving parts. Both need at least 10 diameters of straight pipe to achieve well-established flow and achieve a 1 to 2% accuracy. They are inexpensive solutions for large diameter pipes, particularly for gases. Ultrasonic and magnetic flow meters measure velocity and therefore flow without fluid contact. An ultrasonic meter measures the Doppler effect of a signal passing through a moving fluid to estimate velocity. It works best with a discontinuous fluid, one with bubbles or a solid slurry. A purpose-built unit can achieve plus or minus 2% precision, but you won't achieve that with the strap-on units that you can move around from pipe to pipe. With no fluid contact or moving parts, calibration should be maintained for many years. A magnetic flow meter measures the current created by a conductive fluid moving through powerful magnets, which achieves a plus or minus 10% precision if you have a conductive fluid, so more aqueous than organic. Mass flow meters pass a stream through two parallel tubes which cause the tubes to vibrate due to the Coriolis effect and the Earth's rotation. The frequency and amplitude of the vibration correlate to both flow and density. So this is the only technology that measures directly mass flow rate, not just volumetric flow or velocity. Accuracies of plus or minus 0.01% are achieved without any need for straight pipe lengths, and there's nothing really to wear out. Mass flow meters struggle with multi-phase flow, bubbles, or slurries. While prices have fallen, this is usually the most expensive flow measurement, but I became a big fan of this technology over the course of my career. See the text for more. We can measure the weight of a vessel if its legs sit on load cells, which are strain gauges whose resistance to current flow depends on the weight they support. They achieve a precision of 0.05 to 0.5% of full scale, but the accuracy drifts, so they must be calibrated 2 to 4 times a year. Further, it is essential that the vessel's weight be supported only by the legs and the load cells, so all piping connections must be through flex joints that do not support weight, which adds cost and can be a safety concern. Measuring liquid level is important in almost all process plants and is often a headache. We can try to measure continuous level, 0 to 100%, and point levels, whether a single point is wet or dry. No continuous level sensor achieves better than 1% precision, and all can drift in accuracy or fail completely with the right combination of circumstances. Floats are simple and inexpensive, but they contact the fluid. The electromechanical systems to detect the position of the float, generally either tapes or magnets, have moving parts that can and do fail, and there are spark and fouling hazards. A measured pressure at the bottom flange of a vessel can be translated to a height of liquid above the sensor if the density and the headspace pressure is known. But density is a function of temperature and composition. Headspace pressure can vary, and if solids are present, they can build up on the surface of a diaphragm on a bottom flange and defeat the sensor. Ultrasonic, radar, and laser level sensors measure the time it takes for sound, microwaves, or light to travel to a fluid surface and bounce back. These are non-contact, so they don't wear out, but calibration is tricky because the vessel structure creates echoes that must be ignored. Ultrasonic depends on the speed of sound, which depends on temperature, pressure, and the presence of foam or vapor, so only low vapor pressure liquid levels should be measured. Radar only reflects off of fluids with high dielectric constants, mostly polar molecules, not many organics. Lasers only reflect off opaque fluids, not clear ones. All of these sensors required well-trained technicians to maintain. Capacitance sensors measure the capacitance between 2 points, which is much lower for air or nitrogen than for any liquid. This is very reliable as a point sensor, such as a high-level probe, unless the liquid can splash up on it. Continuous capacitance sensors for a whole tank tend to foul and are difficult to calibrate, so are little used. Vibratory or tuning fork single-point level probes measure the resistance to vibration at one level point and are simple and very reliable. Read more in the text about the difficulties of level sensing. Measuring composition online is generally difficult, expensive, and unreliable because it involves technologies better suited for a lab bench than a process plant, so it is rare. Most processes have to rely on periodic sampling for composition measurement with the delays, sampling errors, and safety issues that sampling can create. Online composition can be possible with a substantial investment in method development and maintenance, and there are a few exceptions where it is possible to correlate a pH or a refractive index to composition at a lower cost. Read more in the text. Today we covered a great deal of sensor technology in a very brief time. I encourage engineers to learn more about the sensors used in their industry and to investigate where improvements can be made. We can't control what we can't measure or react to a hazard that we don't observe. Sometimes out of excessive conservatism, we stick with familiar old technologies when there are better solutions. Look for a full text, exercises, and more videos at chemicalengineeringpractice.org. I'm Tom Meadowcroft. I hope to see you again soon.